Let's get started. Good morning, everybody. Welcome to somewhat smoky overcast Thursday morning of General Chemistry, Chem 1105 at College of DuPage with your host, me, Dr. White. All right, public service announcements from the management, me. First of all, don't forget, right after lab today, I will be sending out the email with the password for your version of test number 3. And you have until 11:30, unless you've received other, what would I say, compensation, not compensation, notification email from me that you can do it later. And a few of you have, but you'll have until 11:30 to take test number 3 and hand it in by uploading it. I like that, uploading it to a, I'm informed today, to Blackboard. Uh, I will by Sunday 1 p.m. if not earlier have your test scores in Blackboard for test 3. I will also by Sunday 1 p.m. or if not earlier send out individual emails with your points for each answer on test number 3. And next Monday, I will go through the answers of test number 3, but I will highlight those visual effects, cut it out of the video because I don't want those answers floating around the internet for all time, especially for when I'm teaching 1105 this fall. Also, don't forget, do the extra credit project. It's optional, but it's 10. Yes, 10 points if you do it right. And you should be able to do it right. What's the reason I'm saying that? Because before you upload it to Blackboard in the assignment area, send me a copy of it via email in advance of the deadline, and I'll check it. If there's something wrong, I'll tell you this is wrong, you got to change it. I'll help you out too. So there's no reason if you want, you can't get 10 bonus points. Remember, you're supposed to do ionic and covalent. And if a molecule has the name of an element that's from the alkali metal, alkaline earth metals, or other metals, it's ionic. I'll say it again. If a name of a chemical or an ingredient has the name of an alkali metal, alkaline earth metal, or any metal, it's going to be ionic. If you have ferric chloride, ferric iron, ionic. If you have sodium chloride, guess what? Ionic. If you have magnesium or sodium sulfate, guess what? Sodium, it's ionic. Now, covalent are a little harder to, but if you don't have a metal name, it's going to probably be covalent. Not always, but if you're not sure, check with me. All right. And we're almost done this semester. Where'd it go? Zoom. We're at the end of, we only got 2 more weeks together, but let's make good use of it. All right. What I'm going to go through today is, first of all, I'm going to go through some material that will be on test number 4. And also, it'll be useful for today's lab. So let's get to it. Oh, one thing I should mention, let me take this down. I will keep the video link open here for Zoom meeting, our normal class Zoom meeting, until about 11:30. If you have any questions, log in. I will be on another computer, so I'll have the screen say something, I'll get my attention, I'll switch over to this computer. Yes, I have 2. Actually, I have 3 computers down there behind me in my office. I'm a power user, if you haven't figured that out by now. All right. One of the things I talked about yesterday, and let me show you. and that is neutralization. And actually, it's a reaction. That's when you take an acid and react it with a base. Remember, acid, proton donor, base, proton acceptor, and you have an equilibrium, and that's why we have, and you get a salt. And these together make a salt, just like Na plus Cl minus make a salt, NaCl. Well, what happens when you do this is you're neutralizing it. Why do we call that? Because if you start out with an acid, remember pH, I taught you yesterday, it's a scale that goes from 0 to 14. At 7, you have neutral solution, or they call it neutral pH. Above 7 is basic, and below 7 is acidic. And when you start out with an acid, as you add base, it's converted to this, and the pH goes up. And if you add the same amount of base, moles wise, as there is acid, you should end up at pH 7, which is neutral, which is why they call this reaction neutralization. Now, neutralization reactions are very useful because you can use it to determine molarity of solutions or how many moles of a solid you have. Neutralization reactions are very useful because they help you determine moles of an acid or base, or whether it's or molarity of a solution. And how do we do that? We do that by what's called acid-base titrations. I will never ask you on a test what is an acid-base titration, but I will ask you to do an acid-base titration problem. Plus, we're going to do 2 labs on this because it's so important. Now, what is an acid-base titration? It's a neutralization reaction in which a measured volume of acid or base of known concentration is completely reacted with a measured volume of acid or base of an unknown concentration. Concentration in this class means molarity. Now, when we do this, we have something called a pH indicator. And this is a compound that exhibits a color, certain color, depending on the pH of its surroundings. And sometimes you'll hear me call it just a pH indicator as opposed to just an indicator. Now, the most common pH and widely used pH indicator is phenolphthalein, and it changes color at pH 7.0, neutral pH. Below 7, it's clear. The solution with phenolphthalein is clear. 1 drop above 7 it's a wine color, almost a reddish purple. And now my sisters would be yelling at me, you don't know your colors. Well, I know my red, green, and blue, but they're right. Which I call wine color. And therefore, if you're adding an acid to base or base to say a base to an acid, you start out clear, and as soon as you see the slight wine color, you stop because you're at pH 7. That's where the indicator comes in. Now, do I have time? Oh, I have time. Interesting story. Phenolphthalein is used as a pH indicator, but for many years, it was the active ingredients in X-Lax, a laxative. And you never wanted a chemist mad at you because he might bring you brownies with phenolphthalein in it, a laxative, and you don't want that. But they found there was the slightest of chance that you might get cancer from phenolphthalein in a laxative, and therefore they took it out and they're using a different one in products that used to use phenolphthalein. So chemicals have many different uses, but the most widely used is phenolphthalein for pH indicator. Now, what a titration does is titration data are used to calculate molarities of acid or base solutions. And the key titration point at neutral pH, when your pH indicator changes, or if you have a way of using a pH meter, when you're at 7.0, you can calculate the moles of known molarity of acid or base. And based on that, we have neutralization reaction. You can determine how many moles of unknown molarity acid or base was present in the volume of the sample of the unknown acid or base. So if you know the volume of the acid or base, unknown acid or base, and the moles in the sample, then you can calculate the molarity of that. And what does that mean, which I don't have on here? At when the pH indicator changes, and let's go to a whiteboard, more room. When you use phenolphthalein, you know pH is 7.0. And the other thing you know, when this happens, when the pH indicator changes color, you know, and this is the most important thing, moles of acid equal moles of base at that time. And one of these, you don't know the molarity. And you can now say milliliters acid, and I've modified this to help you out, times molarity of acid equals milliliters of base times molarity of base. And if I know three of these, and generally either, let's call it A or B, that's the creative, you'll know the milliliters on both sides, and you'll either know A or B. If you know A, you solve for B. If you know B, you solve for A. And that makes titrations very, very useful. Now, there's certain types of titration like this that, depending on the chemical reaction of acid and base, will give you other indications about things you're measuring, including purity. And one company I worked for, when I joined them, I was brought in to be the new lab manager, which meant I managed both research lab in all of North America and at this one plant, which was the plant they had in North America. It was on by 47th and Racine in Chicago, and the plant's still there. It's been bought by another company. But anyways, I also managed a quality control lab, and I'm one of the few R&D chemists you'll ever meet, PhD R&D chemist. R&D stands for research and development, who's ever managed a QC lab. It's not fun, but it's very important. And every morning when I joined that company, the chemist in the quality control lab, which we call QC lab, would do about 75 titrations. Yeah, 75 to get results of the different product tanks we had. And it was not that fun to do all those. And I found a way to automate it to make it go quicker. And it did, and saved the company a lot of money. And now these chemists could do more challenging things, even though titrations are very important. And another company I was hired to improve their quality control lab because of my experience in QC quality control. They were doing titrations the old way, which in a teaching lab, we still do it that way using what's called the burette. All right, everybody see the blue tube on the right of your screen right now? Thumbs up, people. Uh-oh, okay, thank you. All right, this is called a burette. They're not blue, but this helps you. It's like a graduated cylinder, but it has a valve here. The valve is called the stopcock, and you can control how much goes down into a beaker underneath. And it starts from zero up here, and as you add, the liquid goes down, and the difference from where you started to where you ended up allows you to find out how much of an acid or base you've added to another acid or base. Now, when I joined the company, they were using burettes, but from the previous company, which I found out about and used at this new company, let's see if I can find it. Let's see if I can spell right. All right, why isn't it showing me the images I want? Time out for a ah. Bingo, I think I found it. All right, Took me a while. I apologize for that. And let me make sure everybody's seeing what I'm saying. All right, everybody see that complex machine in the right? It's got a green and a gray. Thank you. All right, this is called a dosamat. And this is this is a burette, electronic burette. What they don't show you is this red button here. You can also have a button in your hand. And here's a stirring plate and a sample. And this is a pump. And you can get accuracy to 1,000th of a milliliter. That's really good. That's like a half a drop. And the company I was asked to solve their quality control problems were using old burettes. And I told the president, we need to get dosamats. By the way, they needed about 8 of them. These go for about $5,000, and said, you want me to spend $40,000? I said, yeah, but why don't we just buy one? You'll see what happens. We did, and it did exactly as I said it would, and we bought 7 more. And that helped accuracy, which helped the purity of the products they were making. So let's take a look at the following. And this is for test 4 material. All right, 10 points. What is the molarity of a NaOH solution if it takes 125 milliliters of a 1.50 capital M, you know that's molarity, HCl solution, to change the color of 215 milliliters of a NaOH solution with a pH indicator? And sometimes I'll put instead of that with phenolphthalein. Or I might say a phenolphthalein pH indicator. So how do you do this? Well, good question. Well, you know, the first step, what are we being asked to find? Molarity NaOH. What are we given? 125 milliliters of a 1.50 molar HCl solution. We're also given, we have 215 milliliters of NaOH. So this is a titration. And what do you know? Well, that's an interesting question. Well, for this, you know, when the pH indicator changes color. You're at neutralization, and you know moles acid equals moles base. And you also know from this milliliters of acid times molarity of acid, by the way, I've streamlined this for you, equals milliliters of base times molarity of base. Now, you should know this is an acid and this is a base. And now I can go ahead and say we have 125 milliliters of acid times 1.50 molar HCl equals 215 milliliters of base times, I don't know what the molarity is. Why don't I know that? Because that's what you're being asked to find. You're being asked to, so we have to solve for this. How do we solve for this? We get it alone on one side. What do we have to get rid of? This. How do we do that? Well, two things multiplied, you want to get rid of one of them, you divide by that number. Whatever I do to one side, I have to do to the other side. So I'll do that. And remember, anybody having nightmares seeing me write A divided by A equals 1? It cancels out. So this cancels out. I'm left with molarity of base equals 125 milliliters of the acid times the molarity of the acid, HCl, divided by milliliters of the base. And because I like to, you don't have to, but I do. I'm going to rewrite it because it looks nicer. And I like things to look nice. Now notice milliliters divided by milliliters, I'm left with a molarity, which I'm trying to get a molarity. So I'm on the right track. And now I'm going to pick up my calculator, which I'm doing that now. I have 125 times 1.50 divided by 215 equals, and this is what my calculator shows me, but I know I have to do proper significant figures. Notice this is 3 significant figures. This is 3. Uh-oh, Dr. White's in his rut. And this is 3 significant figures. Therefore, rounding this off to 3 significant figures, I'll let you try that first. Round that off to 3 significant figures. And the answer is keep the 8, keep the 7, keep the 2, use the 0 to round off. That's 4 or less. I drop this. So the correct answer is the molarity of the unknown base, sodium hydroxide, and I should have put here, up here, NaOH. Hold on. And that was my mistake. And that's how you do it. And this is very important. Like I said, the company I work for, all the companies I've ever worked for, they're quality control labs for the plant to make sure the products they make are correct, do titrations. And they're very important. There are things done titration to make sure your fabric softener is correct. I've worked with companies like that. They do titrations to make sure your soap and laundry detergent they make are correct. And many other things are uh, important physical parameters are determined via titration, acid base. Now, one of the important questions is, if I make up a base solution and I don't have any known acid solution, how do I know what the molarity of that base solution is? Good question. And that's a very important question to answer, because most of the not say most of the titrations use molar sodium hydroxide, a base, and you make that up just like I taught you. How many grams do you put in with a certain amount of water to make up a certain molar solution? And we went through that, and it'll be on test 3. But anyways, how do you do that? Well, that's today's lab. And everybody, it's lab time. And today's lab, what is it? It's standardization of NaOH solution with KHP. And this is something done in almost every lab I've ever worked at. You make up sodium hydroxide, NaOH solutions, and you want to know what is the molarity. And you use what's called KHP. Now, first of all, just to be safe, let me get my fast thumbs up, people. Do you see the standardization of NaOH solution with KHP on your screen? Thank you, thumbs up, people. All right, let's take a look at this. If you have a specific molar solution of sodium hydroxide, how do you know, and this is key, accurately, what is the actual molarity of that solution? You do a titration of that solution with a standard monoprotic. That means it only has one proton to give up. In this class, I'm just sticking to monoprotic acids of a known number of moles. And the universally used standard monoprotic acid for standardizing sodium hydroxide is KHP. Everybody calls it KHP. And it's also, the full name is potassium hydrogen phthalate. Say that 5 times quickly. And KHP is a solid at room temperature. Now, when KHP reacts with sodium hydroxide, KHP has an acidic proton. It donates to the sodium hydroxide, and you get a salt plus water. At neutral pH, that's when the pH indicator changes color, the following is true. Moles of KHP equal moles of sodium hydroxide. Now, KHP is a solid, so if you weigh out a certain amount of solid, you learned for test number 2, I have grams of this compound, how many moles of that compound? And you do the following. right here. Moles of KHP equals grams times 1 mole per the molecular weight. Remember how we said if you want to have, if you have grams and you want to go to moles of a compound, moles go on top, grams go underneath, and where do you get that 1 mole equals the molecular weight? And that's what I have right here. Now, being the nice person I am, I give you the molecular weight of KHP. So if you weigh out X grams of KHP, you can use equation 2 to determine the moles of KHP. And what this really tells you is the grams of KHP divided by 204 equals the moles of KHP. And KHP is a solid. Now, one important thing about KHP, it has a tendency to absorb moisture, water. And if you weigh out a certain amount of KHP and it's wet, it's going to throw your calculation off because you think you have so much KHP, but actually have less of it because some of the weight is water. So what do? Whenever you're using KHP, we have in laboratories an oven just dedicated for that, and you put your sample in there. Now you can't weigh samples that are hot. Afterward, you put it in a container called a desiccator. And a desiccator is a container that has a chemical that absorbs moisture, so the atmosphere inside the desiccator is zero moisture. And you put your sample in there to dry out, and then you use it so you know you have dry KHP. It's very important. Let's see if I can find a picture of desiccator real quick. And I did. Everybody see the container? Let me make sure I did this. If you look on your left of your screen, this top comes off. It's got vacuum grease on it. It slides off. Underneath that white plate with the holes in it, this one doesn't have it. You put a chemical called the desiccant in the desiccator. And it's a chemical that normally the ones have used, it's called dry right. And it's got a color in it, a dye, that when it's dry, it's blue. When it's wet, it's pink. And you always want it blue because it's absorbing moisture. And on the white plate, you put your beaker of hot KHP out of the oven and let it cool in there. And then you take it out of here and use it. Now, in the lab with Beyond Lab Z's lab, let's assume the KHP is dry. Now, what you'll do is in a beaker, you'll have KHP and water, and then you'll titrate it. And I'll show you what that means in a second with NaOH of the unknown solution till the color changes. And at that point, you know that moles of KHP equals moles of sodium hydroxide, which is equal to milliliters of sodium hydroxide, which is times moles of sodium hydroxide to molarity per 1,000. Now, for this equation right here, let me make sure. Does everybody see equation 2 and underneath it on your screen right now? Thank you, Ashley. And you solve for NaOH moles, which will be the molarity. And to help you out, don't tell anybody I'm being nice. Shh. You'll use equation 3. This you get from equation 2. This you get from your titration. This is an exact number, and you'll be able to calculate the molarity. And that's today's lab. Now I have the procedure here. Follow it exactly, and I'm going to go through and show you how to do it now. But one of the things, if you look in the syllabus, I have the Beyond Lab Z PDF. And a lot of you got confused the last lab. Am I supposed to do that or not? And I decided not to put it up for this lab or the next because I wrote the lab myself and you don't need that. And if you want, you can find it on Beyond Lab Z or email me. You don't need it. All right, let me open up Beyond Lab Z. All right, everybody should see Beyond Lab Z on your screen. Thumbs up, people, help me out. All right, click on Chemistry Open. And this is in the procedure. Now, don't click on titrations. Watch closely. And let me get, everybody should see the screen that at the top says titrations, calorimetry, inorganic. Thank you, Deanna. All right, now, don't click on these. On the lower left where it says worksheets, click on the arrow acid-base chemistry. Click on the arrow acid-base chemistry. And now scroll down to where it says acid-base standardization under the worksheets. You should see in the center here, determine the molarity of unknown solution of NaOH by titrating against a primary standard potassium hydrogen phthalate, KHP. So I'm going to click on acid-base standardization. It's in your, now everybody, once I let you see it. All right, everybody see the lab with the burette and all sorts. Thank you. Now, this is a burette. This is called a stopcock, or they'll call it a valve. You can open and close it. Now, you need a beaker. Let's put one there. This you don't have to do, but I just want to show you something. All right, now, if you look over in the upper left, you see that this is the sodium hydroxide unknown solution, and that's just the unknown solution you'll be using, and we're at 0.0. You record that. Now, you should, before you do the actual lab, come in here and practice. It's fun. I'm a chemist. And when you turn the valve, see how it's going down? And you can change the valve so it's going slow. It's off. When it's like horizontal, it's off, and you can make it go a little faster, and you can go faster, and you can go real fast. By the way, we call that shotgunning. I don't know where it came from. and you can control it. And that's how you do the lab. Now, first of all, let me exit so it clears everything. Again, click on acid-base standardization. And now here's what you're going to do. This is the actual lab. You take a beaker, open the beaker drawer, click on it. Oh, it's got sound. Put the beaker back here. And in a lab, I would be telling you, make sure you close your drawers because it hurts when you walk into it. And let me do something. Now, click on the scale, the balance. Take a piece of filter paper, put it on the balance, tear it, which means zero it. Now, take the cover off the jar and the bottom spatula on the label, click on it. And now drag this over. And now you want about 2 grams, so you're going to do this twice. And if it doesn't change like it didn't, now it will. Now about 2 grams, 1.9, you'll take the filter paper and dump it in the beaker. Now you'll hit zoom out. You'll take this beaker and put it underneath. This is called the burette. Now you need some water in there. So here's the water squeeze bottle with DI water. And there you go. Now that thing turning in there is a magnet called the magnetic stirring bar. It's Teflon coated. Underneath this base is called a magnetic stir, which has a motor and a big magnet that turns the little magnet in the beaker. In our labs, undergrad, you don't have that, but you use what's called the Erlenmeyer and you mix it by hand. Now, over here, which is useful, see where it says pH probe? The other one says conductivity. Click on the pH probe and bring it. This is sometimes tricky. And put it in there. Now, of all the lab, what I'm going to do next is the hardest part. In the second bottle here, see where I have my mouse pointed over it, a cursor or the hand, says phenolphthalein. Click on that and take the eyedropper. You got to position it right that when you let go, and I didn't do it right, see how it clicked in place? Now I'm going to be adding phenolphthalein, my pH indicator. Now, I'm going to move this over here. And that's a graph of your pH meter showing you the pH. And when it zooms up, you know you finished it. But a better way is watch the bottom of the beaker. And what you do is, first of all, record the volume. I'm at 0.00 milliliters. The bottom of the U is where, remember, each one of these lines, the big line is 1 milliliter. Inside 1, 2, 3, 4, 5, 6, 7, 8, 9. Each one of these small lines is 1/10 of a milliliter. And if you're on the line, that would be 0.00. You're between the line, that would be 0.05. So you can get 3 significant figures here. Now I'm going to open it up, and you should notice I'm going slowly. And if I open up more, I'm faster. I'm really going fast. Now, I'm going to give you a hint. You need to be around 30 milliliters. So you can take 20 minutes getting there, or you can do what someone who's done thousands of titration. I did one this morning to check, and you should get about 30 milliliters. If not, you do the lab over again. It's quick. Now I'm going to stop for a second. If you notice, the pH is slightly climbing. because we're adding a base to the acid, neutralizing it, going to pH 7. Now, here's the skill of a pH, of doing a titration. When you're getting close, you slow it down. Even now I'm going fast, getting near what's called the endpoint. And see how this is starting to arch up, which tells me I'm near my endpoint. Should change color. There we go. And as soon as it changes color, we now have neutralized all the acid with the base. And if we look over here on the upper left, I have 32 point, I'd call that 0.1, 0.2, 0.25. Actually, you can get 4 significant figures now. 32.25. That's my final volume. Now, let's go back to the lab. Jada asked, what liquid did I click? The burette is already filled with the sodium hydroxide for you when you use the acid-base standardization worksheet I clicked on to get to that in the beginning. Go back and look at the video and you'll see what I did. And if you have any problems, always feel free to come to my office hours. Now, like I have here, step 14, when you add the phenol, move the eyedropper till it snaps in place. If it doesn't, you think it added it, but it didn't, and it won't change color. Now, originally, when I weighed out the KHP, I can put in the grams of KHP. My initial run for this one, what I did, A was 0.00. B was, I think, 32.25. And then the volume of NaOH used is B minus A. Now, you have to calculate using equation 2, the molarity of KHP. And then you use that in equation 3 to get the molarity of NaOH. Now, when you're doing a titration, you never do one. You do it in duplicate to make sure you didn't do any serious errors. Because if you did it correctly, both answers should be almost identical. Not identical, but close to it. And that's why, notice, you've got to do that a second time. If you look at step 19, repeat steps 3 through 17 one more time for your second titration. I have you exit the lab, do 19, which is repeated. So you will do 2 titrations, and you will need to calculate these numbers and these numbers. This one in red, this one, you'll get the weight from the balance, and this you'll get during your actual titration. This you'll also have to calculate using, wrong color. So wherever you see a black question mark, that's what you have to calculate. And the others are readings you get from the lab. And for this calculation, you use this. For this calculation, you use this. And for this calculation, you use this. Where are those equations? Here's equation 2, which means you actually use this one. Oh, wait, I was wrong. Here's equation 2, and this is how you get the moles of it. You do this, grams of KHP divided by 204. For equation 3, to get the molarity, use moles of KHP, which comes from equation 2. This is the exact number. This is the milliliters you get from B minus A from your titration. And that's today's lab. It's a lot of fun. If you make a mistake, you can go back and do it again. It's quick. And here's some questions for you to answer. And this lab is due next Tuesday. Any questions? If I look at the clock, boy, did I time it good? Am I good or am I good? Thank you. You're welcome. All right. In about 5 minutes or so or less, I will send out the email to you with the password for test number 3. If you haven't downloaded it from Blackboard, do it. Make sure, unless you have authorization from me to be late, you have until 11:30 today to take test number 3 and upload it to Blackboard. I'll keep this video open, but I'll be on another computer. So if you need help, just call my name and say, hey, I need help, or whatever you want to say to get my attention, and I'll be here to help you if you have questions on test number 3. And with that, I'll say, gang gesund. I'll be sending the email out in a little while, and you should go right now, if you haven't, download it, and also be ready to read your email. Any questions before I turn off the video feed here and go send you your emails? All right, good luck. By Sunday, 1 p.m., I will have in Blackboard, if not earlier, your test number 3 scores, and I'll also have mailed out to you the individual email with your test scores. With that, I'm going to sign off.